Thank you. My name is Átila Saraiva Quintela Soares. I'm a PhD student at the University of Alberta. Let me see if I can use a mouse here. Okay, so here at the University of Alberta. And my advisor is Mauricio D Sacchi, as is in the presentation. And I'm here to present a package that I developed last year called SequentialCompression.jl, out-of-core multi-array compression. I'm part of this signal analysis and imaging group, as you can see here in the corner. So this is the package. I changed the name, actually. So in the schedule is sequential compression. I changed the name to sequential ZFP compression because I don't plan to implement other compression algorithms. So it's just sequential ZFP compression.jl now. And here I use this ZFP compression.jl package as a dependency developed by Milan Kloer, and also tile iteration.gl, developed by Tim Hawley and other contributors. And the package is being registered. It's in the timer for 3 days for the auto merge, but is in the process. So I work with geophysics, and the problem that I have in geophysics is that I have a linear operator that is basically a wave simulation, but it's linearized, so you have like two wave fields actually. So you have the background wave field, this one, which is equal to this one here, and a perturbed wave field. And in the forward simulation direction, I calculate both of these wave fields at the same time. So this is the first iteration, second, third, fourth. So it's okay. We don't have to do anything about it. You just calculate it, and it's fine. But in the adjoint version, you actually go from the last time step to the beginning. But it's inefficient to recalculate this every iteration that you have in the backwards direction. So you go like this. If you had to recalculate the background wave field every time, it's very inefficient. So what we can do, you can just store it. So you can store it in a disk file, whatever. The problem is, if this array is super big and you have many iterations, then it becomes unfeasible. It doesn't fit in memory, neither in disk. Or it might fit in disk, but it might be very cumbersome. So what you can do is use compression. There are other techniques like checkpointing and stuff like that, and many people here might be already familiar with it. But the solution that I propose is just using lossy compression. So this is the problem. Imagine that you have an array of 1,000 by 1,000 by 1,000 with the precision. You have 8 gigabytes. If you have 8,000 iterations in your forward simulation, you use a finite difference. And 100 simulations, 100 shots in this case. It's just a nomenclature from geophysics. And then you have 8 terabytes, or 100 terabytes. And per shot, per simulation, you have 8 terabytes, which is a lot. So how can you reduce that load? So here comes the ZFP compression algorithm. The ZFP compression algorithm tries to create a floating point compression engine that is lossy, and you can control the amount of lossiness that you're comfortable with. And let's talk about it. So the first step is to divide your array into blocks of 4 by 4, in this case because it's 2 dimensions, but it can be 4 by 4 by 4 for 3, and so on. And for any blocks that are incomplete, you just pad with zeros, and it works. And you do a bunch of stuff, like you can convert to signed integers and use a binary representation, base shift plus truncation, linear orthogonal transform, reorder elements, bigger first, convert to nega binary. I'm not going to get into details, but you can always read the paper from I don't know how to pronounce it, from 2019. What you get in the end is a binaries. So we are compressing float 16. So n here is the number, the values in the block. In this case, it's 4 by 4, so it's 16. And we also have 16 in this direction too, because we have 16 bytes or bits. After we've done truncation, we might have less, but let's consider the ideal case that we didn't reduce, so didn't do any truncation. So in this case, here is a bit plane. So this is organized in the rows. These are different numbers. And in these columns, you have bit planes. What does that mean? I did some reordering, and the negative binary representation makes it so that the first bit is always the most significant, which means that if you ignore all of this and you only use this, supposedly you have a lossy representation of your number, And if you use 2, so if you use 2 bit planes, then you have 2 bytes that you're associating with it, and so on and so forth. So imagine that these are the binaries that I already done a bunch of compression here. Now I want to figure out how many bit planes I want to use. So the stopping point for how many bit planes I can use can be parameterized by rate, for instance. In this case, the number of bit planes is limited by the number of bits that I want for each digit in the block, so it's normalized. Precision is the number of bits for the whole block, average. And tolerance is the max absolute error for the whole block, for the values. 3 minutes, all right? Right. 1 minute, oh, shit. So let's be quick about it. So this is the iterative process. So in the first compressor that I developed in memory, so I just compress it, put it to a vector. Here, I compress, I divide into the last dimension, I compress into different files. And the files are limited by the number of threads. Here is some code examples. So I have a compressor here, and I can append a few arrays and check if it's the same. In this case, I'm doing lossless compression, and then I can save to a file and then export low later. Then I can define the type of compression that I want. If I'm using the multi-file, I can define the path, or multiple paths, rate, precision, so on, and tolerance. I can check if the artifacts are conserved. They are. I can check how the space saving goes, and in fact, the space saving is pretty good. So it's a linear relationship for the rate. For the tolerance, it varies with the data. The speed is pretty good, but it varies with the number of threads that you have. So in this case, you have a minor, a lesser execution time per iteration for the final difference if you have a high number of threads, which makes sense. And you can see here that the time per iteration for the multi-file compressor, it's bounded by the just using saving to array and saving to a disk, which makes sense too. So final thoughts. Multi-file compressor offers excellent performance and much potential for further improvement. Probably can compose it with domain decomposition. And there is implementation of the FP algorithm in CUDA, and this might be a future work on it. And I wanted to acknowledge my advisor, my sponsors, Milan Chloe for the SequentialCompression.jl for merging my PR, the audience, and thank you. If you want to take a look at the repository, please do. And thank you for your time.
Thank you for your talk. Questions? So
Thank you.
You used that in simulations, right?
Yeah. In this case, wave propagation simulations.
Yeah. How much in practice can you compress things before the simulations become untrustable?
I only compress the background wave field in this case. So the simulation itself is done uncompressed. I only do for the adjoint part. So this part here. I only compress this one here. So it only affects the correlation between this uncompressed field and this compressed field. So it's not too big of a deal. I made a presentation on another convention, but it was for geophysics, that I showed that the difference is not too big, and you can actually get away with compressing this field. Of course, if you do a very lossy compression, then it becomes bad. But
okay, thank you.